Greetings of the day to all of you. We resume our lecture series on applied power electronics. In the previous lectures, we have been discussing Module 1, which is essentially focused on device physics, different types of power electronic devices, their structure and characteristics. Just a quick recap. Till now, we have discussed about the different devices and their approximate characteristics, how different devices can operate over one quadrant or over two quadrant, and how we can combine various power electronic devices in different configurations to generate four quadrant switches, or two quadrant switches with bidirectional current carrying capability, or two quadrant switches with bidirectional voltage blocking capability. We then moved on to discussing about the device physics behind the operation of power diode and its construction, and this was followed by discussion on SCR. In the next lecture, we moved on to understanding the construction and physics of operation behind power MOSFET and that of IGBT. And finally, in today's lecture, we'll try to wrap up Module 1 with some discussion on GTO, a little bit discussion on IGCT, and some information about silicon carbide or gallium nitride based power electronics devices, which are also known as wide bandgap power devices. Now, before we move on to the next module, I would like to tell you that Module 1 is only an introductory module, because device structure characteristics and device physics are not as essential from the point of power electronics, applied power electronics especially, because later on when we do converter circuits, we essentially treat devices as switches. We definitely need to know their quadrant behavior, what are their voltage blocking and current carrying capabilities, and we treat them as switches that can be turned off or turned on. So device physics structure and structure does not play that vital a role. So we are just brushing through module 1 so we can move on to more important modules. Now, moving on to gate turn off thyristor or GTO, which we will discuss today. So basically, a gate turn off thyristor, as the name suggests, it belongs to the family of SCRs or thyristors. So it is also known as a GTO, is a fully controlled device. It is just like a thyristor. It has an anode terminal, a cathode terminal, and a gate terminal, but the current through the gate terminal can be positive or negative, and positive currents turn on the GTO and negative gate currents turn it off, unlike a conventional thyristor where a gate has no role to play in the turn off process. So basically, a thyristor that has been converted into a fully controllable version by some topological modification, some constructional modifications, it becomes a GTO that can be now turned off through a negative gate current. So it is generally symbolically represented with a cut mark on its gate terminal, or you can also represent it by showing bidirectional gate current. So if you show in the gate terminal bidirectional current, that is also one way of representing a GTO. Now let's move on to the construction of a GTO. Now, how does a GTO look like? So a GTO, basically, it resembles a a thyristor in its construction, because it is essentially a thyristor. So it again has four layers, PN and PN, again represented by the two transistor model. So you basically have a P region which forms the anode of the circuit. So you have a P region followed by an N region, which is a lightly doped region, so N minus. This is followed by again by the P region, and then you have cathode deposits diffused into this p region at many places. And such kind of a structure, this is more diffuse than what is done in a conventional thyristor. So such kind of a structure is known as an interdigitated gate cathode structure. So you have a highly interdigitated gate cathode structure. These gate cathode interdigitated metallizations are present even in case of a thyristor, but it is more interdigitated in case of a GTO. So all these cathode metallizations, the cathode regions, they are all highly doped, and that's why represented by an N plus sign, and they together form the cathode. So this is your cathode terminal. And the p region over here, say all of this region, is, because it's the same, the medium is the same all over here, this forms the gate. The top region over here, the one connected with the p side, is the anode region. Now the N minus region, it has certain protrusions into the p region like this, and those protrusions are highly doped, so they are N plus, unlike the bottom part which is lightly doped. So when you're talking about 4 layers P and Pn, the second layer, that is the N layer, which is basically N minus layer, it has some protrusions into some diffusions or protrusions into the P region and far into the P region, so that they're shorted with the anode, and these are known as the anode shorts. So we are basically essentially making some small modifications in the structure of a thyristor, just so as to ensure that we can get turn off capability and fast turn off, that too a fast turn off. Now primarily a gate turn off thyristor or a GTO differs from a simple thyristor or a simple SCR by 3 things. The first thing is that you have a highly interdigitated gate cathode structure. You're basically increasing the cross section or the length of the gate cathode junction by introducing a number of cathode structures diffused uniformly onto the P region. So it has a highly interdigitated gate cathode structure. That is one difference as compared to a thyristor. The second difference is that these cathode regions, because this is basically a 3-dimensional structure, I've drawn a 2-dimensional diagram, but it is essentially a 3-dimensional structure. So wherever there are these cathode deposits, these N plus regions, the silicon area around them is etched away, so they come out as protrusions. They are, you can say, they are embossed above the surface of the wafer. If you want to see a clearer diagram, you can see it on Nedmohan. It will give you a better idea of showing how the area around these diffusions around these cathode regions is basically etched away, and they come out of the surface. So that is about the cathode region, how it is they are etched in the form of islands on the surface of the wafer. And the third difference is that the second layer, that is the N minus layer, is protruding into the anode region through N plus regions basically. So there is difference in doping concentration. There is highly doped region intruding into the P region and shorted with the anode terminal through anode shorts. So you have anode shorts. That's the third difference when you compare it with a thyristor. Now if we see a gate turn off thyristor and we want to observe its behavior during turn on and turn off, let's see basically how does this device respond to turn off and turn on. So you have the turn on response of a GTO. A GTO turns on just like a thyristor. To understand it better, you can refer to the two transistor model, where we all have already discussed it in the previous lecture, where your thyristor or your GTO, because they are essentially again four layers, PNP and NPN. So you have PNP and NPN connected back to back, something like this. The collector here is connected to the base, the collector here is connected to the base, and this is the emitter of one transistor, this is the emitter of another transistor, and here over here is your gate region. So if you observe this structure, they are similar. Again, you have the two transistor model. When you inject a gate current into the P region, that is here, when you make this positive, it ensures that your transistor, one of those transistor, gets a sufficient gate drive, and it goes into, sorry, a base drive, and it goes into conduction. Its collector current flows, and due to the flow of this collector current, the first transistor goes into saturation, and its collector current flows. That in turn increases the base drive. It's a cumulative positive feedback process, and both those transistors go into conduction eventually. So the turn on process, we are talking about the turn on process. The turn on process of an SCR and that of a gate turn off thyristor are more or less the same. Now the difference lies in the fact that a gate turn off thyristor or a GTO can actually be turned off through a gate current. Now you need to remember some things, is that in order to turn off a gate turn off thyristor, you need to inject a gate current that is significantly high in magnitude. Generally, when devices are carrying amperes of current, anode cathode current is in the range of amperes, the gate currents are very small in the range of say milliamperes. But in case of a gate turn off thyristor, to turn it off, you need to inject a negative gate current, and that negative gate current has to be a very high magnitude negative gate current, almost as much as 1/3 the value of the anode current that is already flowing through the device. So if your GTO is on, it is conducting an anode current, that is the current flowing from the anode to the cathode. The device current is say 100 amperes. Then in order to turn it off, you need to inject at least minus 30 amperes of gate current, which is high magnitude of gate current. Now high magnitude of current flowing through the gate driver circuit makes sure that you have high power losses in the gate driver circuit. So that is one of the reasons GTOs generally do not operate at high switching frequencies. You operate them at low switching frequencies of the order of hundreds of hertz, say 200 to 300 hertz. You can even go up to kilohertz range, but generally GTOs are preferred to be operated in low switching frequency, because they incur a lot of losses. Their turn on and turn off times are also slow, and that also increases the losses. And moreover, they have losses in the gate driver circuits, because the negative gate current that turns the device off is high in magnitude, and obviously it will cause more losses in the gate circuit. Now what happens when we inject a negative gate current? So basically how we inject a negative gate current is that we make the gate terminal negative with respect to the cathode, highly negative with respect to the cathode, as a result of which the current, anode current, abhi device on tha, to anode current was flowing in this direction from the anode, injected PN into the cathode, something like this. But this the injection of holes, what your intention is that you have to turn the device off. So you have to wipe off all the carriers, diminish those carriers, and then your device will turn off. Now the majority carriers in this P region, those are the holes, they will get attracted towards the gate. So the gate side, the gate current will be the gate terminal will actually intercept a part of the anode current and flow in the form of a negative gate current. तो negative gate current की वजह से यहाँ से जो भी आपके holes होंगे, they will get depleted. And all these the interdigitated gate cathode structure, it actually helps in intercepting all that anode current and diverting it towards the gate and causing a faster turn off. So highly interdigitated gate structure is actually helping you turn off the device through a negative gate current, of course. Another thing is that जो आपके n minus region में carriers होंगे, minority carriers से, which are your holes n minus region में, ये जो n plus protrusions हैं जो shorted हैं आपके anode के साथ, these n plus protrusions will act as sinks for these holes. Now how will they act as sinks for these holes? So this region, this n minus region is lightly doped, यानी कि यहाँ पे आपकी जो कैरियर कॉन्सेंट्रेशन है वो लो है, और यहाँ पे जो आपकी कैरियर, आई एम टॉकिंग अबाउट द मेजॉरिटी कैरियर्स n प्लस रीजन में, वो आपकी कैरियर कॉन्सेंट्रेशन हाई है. बट द रिवर्स थिंग विल हैपन फॉर द माइनॉरिटी कैरियर्स, यानी कि होल्स जो है वो यहाँ पे ज़्यादा होंगे n माइनस रीजन में, क्योंकि यहाँ कम डोपिंग है. द माइनॉरिटी कैरियर्स अ फ्यू इन नंबर बट दे स्टिल एग्जिस्ट. और n प्लस रीजन में आपके जो माइनॉरिटी कैरियर्स होंगे, होल्स, वो कम होंगे, यहाँ से ज़्यादा होंगे और यहाँ की तरफ कम होंगे. तो द होल्स जो भी माइनॉरिटी कैरियर्स हैं n माइनस रीजन के, they will be synced into the n plus region and obviously taken away from the device because there is an anode short. So anode short actually also intercepts your carriers and takes them away through a diffusion process. अब अगर ये नहीं होता, let's talk about a thyristor, जो simple thyristor था, वहाँ पे आपके n माइनस रीजन के दोनों साइड से p रीजन्स थे जहाँ पे होल्स की कॉन्सेंट्रेशन बहुत ज़्यादा थी. तो ऑब्वियसली होल्स विल नेवर मूव फ्रॉम, एनी कैरियर विल नेवर मूव फ्रॉम लो concentration to high concentration, but they will move from high concentration to low concentration. That's the essence of the diffusion process. Now if you have a n plus protrusion which has a low concentration of holes, obviously the holes will move from n minus region towards n plus region, the minority carriers I'm talking about, and they will get diffused away. So basically this structural modifications have helped you in achieving a faster turn off for the device. बट बिसाइड्स दिस आपका डिवाइस भी ऑफ हो गया, सो यू आर गेटिंग फुली कंट्रोल डिवाइस. बट अपार्ट फ्रॉम दैट देर इज सम प्रॉब्लम दैट दिस मॉडिफिकेशन हैज़ कॉज्ड, एंड दैट प्रॉब्लम इज़ कि जब आप इस स्ट्रक्चर को रिवर्स बायस देते हो, सो दिस इज़ योर पी रीजन, इसके अंदर आपके एन के प्रोट्रूजन्स हैं like this, n plus protrusions, and they are then you have the n minus region over here, and then you have the p region, and उसके अंदर आपके again interdigitated cathode region है. So this is your cathode, and then this p region is your gate, and then whole of this is your anode. अगर हम इस डिवाइस को पॉजिटिव वोल्टेज देते हैं, वी आर टॉकिंग अबाउट जी टी ओ, और एनोड कैथोड हम पॉजिटिव वोल्टेज देते हैं, इट कैन ब्लॉक दैट पॉजिटिव वोल्टेज जस्ट लाइक अ थायरिस्टर. अनलेस यू गिव इट अ गेट, these will not go into conduction, so positive voltage can be blocked by a GTO. And once you give it a gate, it will go into conduction, and when it conducts, it will carry only positive currents. अगर आप थायरिस्टर की बात करो तो वो एक नेगेटिव वोल्टेज भी ब्लॉक कर सकता था, बिकॉज व्हेन यू गिव नेगेटिव anode, when you make the anode negative with respect to the cathode, when you reverse bias a thyristor or this device, what used to happen in a thyristor, that two junctions used to be reverse biased and one junction used to be forward biased. जब दो junctions reverse biased होते थे, उसकी वजह से आपको रिवर्स ब्लॉकिंग कैपेबिलिटी मिलती थी. लेकिन यहाँ पे जब हम आप रिवर्स बायस करते हो, ये जंक्शन जो आपका ये वाला जंक्शन है, पहला पीएन जंक्शन, लेट्स कॉल इट जंक्शन J1, इट गेट्स कम्प्लीटली बाईपास्ड बिकॉज यू हैव थ्रू दिस n plus protrusion or diffusion, you have this region coming directly in contact with the anode through the anode short. तो आपके anode को ऐसा लग रहा है कि this minus region is actually connected to the n part. So this NP, it is forward biased. You have bypassed the first junction. J1 has been bypassed. Junction J2 is forward biased, and now it is only J3 which is reverse biased because your cathode is at positive terminal. So this is positive, this n region is positive. तो आपका जो J3 है, सिर्फ ये वाला जंक्शन है जो रिवर्स बायस्ड है. तो अब क्या होगा कि आपका जो GTO है, इसकी जितनी भी रिवर्स ब्लॉकिंग कैपेबिलिटी है, दैट इज़ ओनली बिकॉज ऑफ जंक्शन J3. दैट इज़ वाई दे कैन नॉट ब्लॉक वेरी हाई मैग्नीट्यूड्स ऑफ रिवर्स वोल्टेजेस, ओनली अप टू 20 to 30 volts. in most cases, and the reverse blocking voltage capability is reduced because of these anode shots. And on the contrary, these anode shots are also giving you the benefit that they are helping in turning off the device when you inject a negative gate current. So there has to be a compromise. Thoda sa ye aapke they modify your characteristics. They give you negative voltage blocking capability, but iski itni zyada negative voltage blocking capability nahi hai. So this was about a gate turn off thyristor. There is another device belonging to the family of gate turn off thyristors, or thyristors for that matter, and they are very relatively new devices. Okay, before we move on to those, I would like to mention that you can study GTO from the book by Ned Mohan, or you can study, there's a complete chapter on GTOs. Then you can also study, there is an application note from Mitsubishi Electric. That's a company that manufactures GTOs and many other electric items. So there is an application note on gate turn off thyristors by Mitsubishi Electric. You can refer to that also. Now the second device that we have to discuss for today is the IGCT, also known as the integrated gate commutated thyristor. Now this device is relatively a very new device, and you can say it's in its infancy right now, not very popular, but it has some promising applications. So hopefully in the near future you can see more of these devices being used. So IGCT was, I think, invented in 1997 together by ABB and Mitsubishi. A combination of two companies have together patented the construction of IGCT, which is essentially the same thing as a GTO. However, जो GTO है, I already told you it, although आप GTO में कुछ modifications करते हो to fast to make the turn off process fast, but in order to kill a very high magnitude of anode current, you need a very high magnitude of negative gate current, जिसकी वजह से GTO में losses भी बहुत ज़्यादा होते हैं. तो GTO में ओवरऑल जो है आपका टर्न ऑफ टाइम और टर्न ऑन टाइम कम ही होता है. बट IGCT जो है, इट इज़ स्लाइट मॉडिफिकेशन ऑफ द सेम स्ट्रक्चर GTO, where you basically ensure that you inject a very high magnitude of negative gate current, so high that it is more in magnitude than the anode current itself. और उसकी वजह से आपको बहुत ही ज़्यादा फास्ट टर्न ऑफ मिलता है. लेकिन क्योंकि जो IG है आपकी वो बहुत हाई मैग्नीट्यूड की है, एंड इन एन IGCT इट इज़ इवन ग्रेटर इन मैग्नीट्यूड देन द एनोड करंट, तो उस वजह से क्या होता है कि आपको जो अपना गेट सर्किट है, इट हैज़ टू बी इंटीग्रेटेड ऑन द सेम वेफर एज the main device, the power terminals, that is the anode and the cathode, as a result of which जो भी आपकी गेट ड्राइविंग वायर्स होती हैं, गेट ड्राइविंग सर्किटरी होती है, जनरली वो आपके नॉर्मली आपके डिवाइसेस में दे आर फेड थ्रू वेरी थिन वायर्स. बट इन केस ऑफ IGCT, if you're driving in IGCT, it has to take a very high magnitude of negative current, so its gate driving circuitry or its gate wires, they have to be of the same thickness, and they have to be of the same current carrying capacity as its main power terminals. Again, इसमें भी gate power losses, they are slightly more because of the high magnitude of gate current flowing through it, but because the turn off process itself is fast, तो उसकी वजह से power losses थोड़े से कम हो जाते हैं. So it's like a trade off. Now जो IGCT है, and that is has found applications in some type of drive applications, especially current source converters. It is symbolically represented by just like a thyristor. So you have a gate terminal, bidirectional obviously, because you are turning it off like a GTO, but ये आप एक symbolic modification करते हो to represent it like an IGCT. So I think this is about IGCTs. This much of information is enough about them. Now we'll end this lecture by a brief discussion on wide bandgap power devices, which is the future of power electronics. So a brief introduction to silicon carbide and gallium nitride HEMTs, high electron mobility transistors. So these are basically wide band gap power electronics devices. One of the most promising technologies coming out of power electronics, which is still again in its infancy. Not a lot of work has been done on them, and a lot of work is being done on these devices. So before we move to these devices and a brief introduction on them, I would like you to, I'm sure you already know it, but I would like you to revise this a bit. If we talk about insulators, at the atomic level, you know that an insulator has a valence band where you have valence electrons, and in order for any material to conduct, the electrons should escape the valence band and go into the conduction band, and they must absorb some energy to make this transition, to make this jump from the valence band to the conduction band. In case of insulators, this band gap, that is the amount of energy that they need to absorb to go into conduction band, is very, very, very high. So the band gap is extremely high, it's very high in magnitude. So that is precisely why you do not have free electrons available to ensure conduction. When we talk about conductors, there is no band gap at all. So electrons are freely moving in between the conduction band and from the valence band to the conduction band. So essentially, if you take a piece of a conductor or a metal, you can visualize it like a sea of electrons, and electrons are flowing to and fro because they do not even need to absorb any energy to be able to drift through the surface of the conductor. The difference between semiconductors and conductors lies in the fact that although semiconductors do not have any band gap, but conductors do not have any band gap, but semiconductors do have some finite band gap, some small band gap. यानी कि जो आपके इलेक्ट्रॉन्स वैलेंस बैंड में है, वैलेंस बैंड इज़ द आउटर मोस्ट शेल ऑफ द एटम, जो इलेक्ट्रॉन्स आपके वैलेंस बैंड में है उनको कुछ फाइनाइट एनर्जी जो है दैट दे हैव टू absorb some amount of energy, and then they can go into conduction, and they can go into the conduction band and conduction can begin. So this is about semiconductors. जैसे कि आपके जो कन्वेंशनली अभी तक सेमीकंडक्टर्स यूज़ हुए हैं, यू हैव यूज सिलिकॉन मटेरियल, यू हैव यूज जर्मेनियम, एंड देयर इज़ आल्सो अ ट्रेंड टू यूज़ गैलियम आर्सेनाइड इन सच सेमीकंडक्टर मटेरियल्स, जो ये प्रॉपर्टी दिखाते हैं कि वैलेंस बैंड से कंडक्शन बैंड में देयर हैज़ टू बी अ डेफिनेट स्मॉल बैंड गैप जो उनको ओवरकम करनी है फॉर फ्री इलेक्ट्रॉन्स टू मूव टू द for valence band electrons to move to the conduction band and become free electrons. Now, when we talk about wide band gap power devices, power electronic devices, they are not made of silicon or germanium or gallium arsenide, but they are made up of either silicon carbide, so which is a compound of silicon and carbon, or they are made up of gallium nitride. Now, they show an interesting property that जो आपके wide band gap power devices हैं, silicon carbide और gallium nitride, they have a wider band gap as compared to conventional semiconductors. So this is your valence band, this is your conduction band, and they have a wider band gap. They are also called WBG devices in short. On the contrary, if you talk about your conventional semiconductor devices, इनकी जो band gap होगी वो थोड़ी कम होगी, slightly less as compared to your wide band gap devices. यानी कि सेमीकंडक्टर्स को, कन्वेंशनल सेमीकंडक्टर्स को, सिलिकॉन, जर्मेनियम, गैलियम आर्सेनाइड, इनको कम एनर्जी अब्सॉर्ब करनी है so that your free electrons are generated. That means electrons move from valence band to conduction band. On the contrary, wide bandgap devices need to absorb more energy. Their bandgap is much less as compared to insulators, but greater than that of conventional semiconductors, as a result of which they have to absorb more energy in order for the electrons to move from the valence band to the conduction band. In other words, we can say that they can tolerate, these devices can tolerate higher magnitudes of electric fields. In other words, I can say that they have higher voltage blocking capability. Higher magnitude of electric fields को ये withstand कर सकते हैं, यानी कि higher voltages को ये withstand कर सकते हैं, यानी कि इनकी higher voltage blocking capabilities होती हैं. In other words, I can say that अगर एक सिलिकॉन डिवाइस है, सिलिकॉन मॉसफेट है, और सेम साइज का सिलिकॉन कार्बाइड मॉसफेट है, तो जो सिलिकॉन कार्बाइड मॉसफेट होगा उसकी रेटिंग सिलिकॉन से ज़्यादा होगी. इट विल बी अवेलेबल इन हाई वोल्टेज रेटिंग. Conversely, the same statement can be said that for the same voltage rating, if I want a same voltage rating of device, तो silicon MOSFET अगर इतना बड़ा है तो silicon carbide छोटा होगा. It will be smaller. If the size is same, then SiC will give you a higher voltage rating, higher voltage blocking capability. And if you want the same voltage, वही 1000 वोल्ट आपको ब्लॉक करना है, same voltage blocking capability चाहिए, then SiC will be much smaller in size. And when devices are smaller in size, their capacitances between their gate drain, gate source terminals are also small. And because those capacitances are small, when you inject gate current, a constant gate current into them, this is constant. अगर C स्मॉल हो गया तो dV by dt राइज हो जाएगा. यानी कि इन डिवाइसेस में जो छोटे डिवाइसेस होते हैं उनमें क्योंकि ये जितनी भी कैपेसिटेंसेस इंटर डिस्पर्स्ड होती हैं दे आर स्मॉलर इन वैल्यू, तो उसकी वजह से उनके dV by dt फॉर अ कांस्टेंट गेट करंट देयर dV by dt इज़ इंक्रीज्ड. और dV by dt इंक्रीज होने का मतलब है कि फास्ट वोल्टेज उस सर्किट में राइज एंड फॉल होती है. सिमिलरली फास्ट करंट राइज एंड फॉल होता है. सो द ट्रांजिशंस ऑफ वोल्टेज and current through these devices are fast, as a result of which you can switch these devices at very high switching frequencies. So smaller devices can always be switched at higher switching frequencies and they will not incur more power losses. जब आप किसी device की बात करोगे, I just want to explain one small concept. If there is a device that is turning off, so its current, it was carrying some current and the current fell gradually and it fell to, ideally it fell to 0. And during this process, we are talking about the turn off process, and during this process initially the voltage was 0 when the device was conducting, it was on, and then when the device turned off some voltage got applied across the device. So this is the turn when it is completely off and this is when it is completely on. तो जब device ऑन होता है देर इज़ नो वोल्टेज बट देर इज़ करंट, सो देर इज़ नो पावर लॉस. और जब डिवाइस ऑफ होता है देर इज़ वोल्टेज बट देर इज़ नो करंट, सो देर इज़ अगेन नो पावर लॉस. बट एज द डिवाइस इज ट्रांजिशनिंग from on state to off state, during this interval the current is falling, the voltage is rising, you have both V and I, so you have the product of these, you have power loss happening across the device, which is your switching power loss. अब कोई ऐसा डिवाइस होगा जिसमें बहुत फास्ट स्विचिंग होगी, यानी कि करंट बहुत जल्दी फॉल होगी और वोल्टेज बहुत जल्दी राइज होगी. फॉर सच डिवाइसेस द स्विचिंग पावर लॉस विल ऑब्वियसली बी लेस, बट द एनर्जी लॉस विल बी लेस बिकॉज द टाइम इंटरवल itself is very less. That is the essence of using wide bandgap power devices. The current falling and the voltage rising, this happens for a very short interval, and when this happens for a very short interval, the power losses in these devices, the switching power losses are drastically reduced, which makes them much more efficient as compared to their conventional silicon or germanium or gallium arsenide devices. So why this is more relevant is because as we are moving towards high power applications where we are handling power of the order of megawatts in power electronic systems, वहाँ पे आपका 1% भी अगर efficiency improve हो जाती है, it is a significant thing, because if you're working with say 100 megawatt and your system is 99% efficient, you still have 1 megawatt of power loss, which is huge. When 1 megawatt, in order to that much of heat produced in a system, it's very difficult to dissipate it. You need huge heat sinks for that. बट अगर आप सिलिकॉन कार्बाइड जैसे डिवाइसेस यूज़ करते हो, आप ड्रास्टिकली अपनी एफिशिएंसी को इम्प्रूव करते हो, एंड इट इज़ मोर रेलिवेंट एंड मोर यू कैन से उसकी सिग्निफिकेंस और ज़्यादा बढ़ जाती है इन एप्लीकेशंस वेयर देयर इज़ हाई पावर इन्वॉल्व्ड. सो इट मेक्स योर सिस्टम, आपको हाई पावर डेंसिटी भी मिलती है बिकॉज योर डिवाइसेस आर वेरी कॉम्पैक्ट. सो छोटी स्पेस में बहुत ज़्यादा पावर हैंडल करना पॉसिबल हो जाता है बिकॉज लॉस भी कम है. तो ऑब्वियसली यू कैन रिड्यूस द स्पेसिंग ऑल्सो. आपके पैसिव्स का साइज़ जैसे एल और सी होते हैं, उनका साइज़ भी रिड्यूस हो जाता है. सो मोर और लेस इट डज नॉट जस्ट गिव यू a couple of advantages. If you see it as a package, it has many advantages to offer, and in applications like electric drives, renewable power conversion systems, or integrating them to the grid, all of these applications you can see wide bandgap power devices becoming the future of power electronics in the coming years. So with that, we end our lecture series on module 1, and we'll move on to the later modules. And please keep me updated about any feedback or any suggestions or queries that you have on the WhatsApp group. Wishing you the best of luck. Good day.